Ricardo, please can you share your screen? And after Ricardo's presentation, we will have a break. So Ricardo is going to talk about a work that we have successfully published recently in Computers in Fluid. It's about gravity current, and I'm sure a lot of people here are familiar with the spectral vanishing viscosity that we are doing in X-compact 3D via the second order derivatives and playing with the numerical error of the scheme. And in this work is going to is going to present some gravity currents using this spectral vanishing viscosity approach. So please, Ricardo, you have 15 minutes.
Okay, can you hear me well?
Yes, and we can see your nice background as well.
Okay, cool. Okay, so thank you, Sylvain. Hello, everyone. So I'm Ricardo, and I'm speaking from Paris at the DynFluid laboratory today. So I will present a work initiated in the end of my master thesis, and after a long time is finally out, recently accepted in Computers and Fluids 2021. The title is High Fidelity Simulations of Gravity Current using a high order finite difference spectral vanishing viscosity approach. It's a collaboration between myself, Georgios Descos, Sylvain, and Georges Silvestrini. So we came a long way since we started putting all of these pieces together in the early stages of X-compact. And it's very nice to see all these efforts consolidated in a unified, accessible open source solver. And somehow we are finally moving into a community code base. So it's pretty cool. Okay. So I start with a quick introduction to gravity current, some definitions and characteristics. It's a gravitational phenomenon, typically developing when heavy fluid propagates into a stationary medium. In the class of buoyancy-driven, transitional, stratified turbulent flows with different areas of interest. So we have safety issues, imagine pyroclastic fluxes, submarine cable ruptures, dam collapses. We have several accidents in Brazil in the last years. Propagation of contaminants, even in geology with formation of hydrocarbon reservoirs. So these currents are characterized by a well-defined shock, which we refer to as the head of the current, which moves horizontally along the bottom with a front velocity UF. So several theoretical and experimental studies, starting long ago with von Karman in the 40s, try to understand the behavior of this front velocity. So nowadays we know that different regimens are expected, a rapid acceleration phase, then the current settles into a slumping with constant velocity phase, and it moves into an inertia dominated phase, reaching after a viscous dominated phase until termination. So you can see here in the slides some Google examples. So we have a laboratory experiment of a saline current flow in a freshwater tank. We have a dust storm created by cold air flowing in a city, avalanche in the mountains, and even a building collapse. So as you can see, real-life examples usually contain very large range of scales and very high Reynolds number, easily over 1 million. So the motivation of this work is to investigate the use of LES, especially spectral vanishing viscosity method proposed by Eric Lambalet, to produce high Reynolds number simulations of gravity currents. And therefore, our objective was to compute first with DNS the highest Reynolds simulation with experimental data in the literature, and then carefully compare all available quantities, ensuring the code correctly reproduce the physics. And then we moved to LES with SVV. Then we try to understand the effects of the control parameter nu0 over nu, and we additionally decided to compare the performance of explicit LES models, namely the Zmagorinsky class. So we focus now on the lock exchange, or also known as lock release flow configuration. The problem setup consists in the sudden release of a fixed volume of heavy fluid into a larger body of less dense ambient fluid. Here, HOC represents the heavy fluid density, HOA the ambient fluid. In space, we consider 1, the streamwise direction, 2, the vertical direction, and 3, depicted in plane, the spanwise. We impose a wall on the bottom, free sleep everywhere, and also for the density and spanwise periodicity. So we mimic the experimental lock removal by adding white noise, modulated at the gate position, and with these two, we add this to accelerate the turbulent breakdown in the simulation. And here the governing parameters are the Reynolds number, the Richardson number, and the Schmidt number. And to define a global or bulk Reynolds number, we estimate a buoyancy velocity, UB, by assuming an implicit balance. And due to the selection of characteristic length scale here, the Richardson number is conveniently simplified to unity. So, and the Schmidt number, analogous to the Brun number, relates the kinematic viscosity nu and the mass diffusivity kappa of the stratifying agent. So, the governing equations are the incompressible Navier-Stokes for viscous fluids, coupled with a density transport equation under the Boussinesq approximation. So here the momentum diffuse, this momentum diffusion term D is case dependent. For DNS, we have the classical Laplace operator. For explicit LES, dissipation is additionally supplied via the eddy viscosity nu T, which translate the subgrid scale stresses as a function of an explicit model based on physical space. And for the SVV case, additionally to the Laplacian, we have a term containing a hyperviscous kernel KC, which we use to construct in the spectral space the SVV operator. And thanks to the second order derivative, those effects are translated into the physical space. So the density diffusion term T for the other equation and the turbulent diffusivity kappa T are defined in a similar fashion, so we don't present it here. And also please note that I make no explicit reference to filtered quantities, but in an LES context, those are formally filtered. So we reproduced experiment number 6, reported in the JFM of Fragoso 2013, which consists in a lock release at Reynolds 31,000 made with sugar and water. And of course, we use the finite differences framework X compact 3D. And thanks to its excellent performance, we are able to maintain the same Reynolds, but unfortunately, we have to simplify the Schmidt. So we use a regular mesh with over 800 million degrees of freedom to ensure a mesh-independent solution. And the estimated grid spaces in wall units are around 1 in the horizontal direction and 0.5 in the vertical direction. So we are well resolved in space and time. And this estimation is obtained by calculating the maximum value of the span-wise average wall shear stress over time. Okay. So here we can observe the span-wise average density field at 2 different times for DNS and the experiment 6. So we identify very similar evolutions in terms of shape and speed. And the Kelvin-Helmholtz rows are present in the simulation and even look a little bit sharper in the DNS. So we expect the experiment to be more diffuse as the large Schmidt in the experiment tends to smooth out the small scale structures. But the head of the current has a very similar shape, and being slightly more concentrated in the simulation, you can see a little darker red. That suggests that the current might carry more energy in the DNS. So we attribute this difference to the initial conditions, which cannot be fully reproduced in the simulation. Imagine in the actual experiment, they do a very abrupt removal of the lock, and we are basically adding white noise. So we have this discrepancy there. Okay. So to track the evolution of the front position, we use a simple reverse search on a line average along the streamwise direction. The front velocity UF, you can see the middle plot, is simply the time derivative of this search. And note that the experimental values have been extracted from the supplemental video given in the website of the publication. And again, we can observe a very excellent agreement between the experiment and DNS. For the DNS, it's nice to see this acceleration phase, like from rest to maximum velocity. It peaks at time 1.5, and then is followed by a small deceleration up to time 4. Then it enters a nearly constant slumping phase. And from time 14, it enters in the self-similar inertial phase. And we can see the exponent there. And then the velocity in the end decreases at an even faster rate when the current reaches the viscous phase. So again, we can indeed recover the exponents predicted in the literature for inviscid theory. And additionally, we show a grid space divided by Kolmogorov scale obtained by the turbulent dissipation rate, which we computed by removing the span-wise average mean at each time step, and then we plot the maximum value here. So for example, for the vertical direction, the condition delta over eta smaller than 2 is satisfied throughout the simulation. And we also noted, interesting, during the majority of the simulation, the most critical conditions are always located in the head region. So in the end, we will show total energy and mass conservation confirming the adequate resolution of the DNS. So for LES, we assume the same time step, so we have no extra effects for time discretization. And we use a very good resolution of 0.4% of the DNS, which ensure a delta X plus max around 15 in the horizontal direction and 2 in the vertical direction. So this fine mesh was found stable for all models without the use of numerical clipping to control the density field or some explicit velocity filtering. And I think this metric was key factor in this work. And it actually, we focus on this because we wanted a pure model action. And because also in other works, they tend to mix explicit modeling with upwinding the nonlinear term to keep things stable. So we wanted to have like a good comparison, keeping the pure model action. Okay. So about the model parameters, for the SVV, we use the optimal parameter nu0 over nu equals 60. So which was found via a physical scaling estimation based on a Paul-like spectral closure proposed in the work of Thibault in 2017. So we also identified minor influences in the range 15 to 90 in a sensitivity study that we also present. For the static Zmagorinsky model, the constant coefficient we use CS equals 0.15 was obtained in a preliminary study. And I think this value also matches the theoretical proposition from Lilly in 67. For the dynamic coefficient, it is computed at each time step. It's filtered and then averaged in the spanwise direction before being applied. So in this plot, we can see that the SVV matches very well the DNS, while the explicit models are either entering too early or too late in the self-similar phases. So the dynamic model is producing a current that goes a little bit too fast, and the static model a current that moves a little bit too slow. Okay, so here we can visualize the isocontours of key criterion overlap with density field at a fixed time. In the upper picture, we can see very fine, very rich and fine structures in the DNS along of the head and the body regions. And quite remarkably, all LES reproduce the big rows being convected and the overall structures of the current. SVV is matching the DNS very nicely in the position, and the other models are a little bit delayed. We also note some spurious oscillations on the static version in the body of the current between the X 3.5 and 6. So here we have the friction velocity maps for also a fixed time. So this is a quite challenging quantity for LES, given we don't specify any explicit wall function. So you can see clearly that the static Zmagorinsky is over-dissipative near the wall, which is somehow expected. And the dynamic Zmagorinsky ended up being too noisy. So from this plot, we can see that the SVV matches much better the amplitude, even though it has some localized higher values on the head region. Okay. In time. So now we look into the proposed energy framework. So this is extracted from the governing equations and allows us to understand how energy behaves in the flow. So we use a potential energy partition concept proposed by Lorentz in 55, which splits the potential energy into available and background partials. The background energy is formally defined as the minimum potential energy attainable through an adiabatic redistribution of the density field, and basically it represents the final equilibrium energy state that the current will reach. So this quantity is computed externally with a PDF method as a post-processing tool. And this split of energy is convenient because it can help us to distinguish between the steering, which is a large scale and reversible process, to the mixing, which we assume as a small scale irreversible process taking place in the current. So you can see on the upper right, we have the energy balance expression, which is normalized by the total potential energy at the initial time, and this should be conserved. Here, all quantities are integrated in the whole domain. And if you see the schematic on the left side, so you can see that we have two routes are available for the energy conversion. So assuming the available potential energy PA on the top, where energy lies on the initial condition, and the final state, PB, which is the final state when the current is finally suppressed and stopped. So we have two routes. The first route is a longer route with multiple stages, you can see on the left, and this is associated with steering. So kinetic energy K is modified by the vertical buoyancy flux omega. You can see this tiny VARP symbol, which will affect the internal energy by viscous dissipation, epsilon, and ultimately the background energy via the density diffusion phi. So this is the steering route, and we have the second route, which is a direct route known as irreversible mixing. And here, energy can directly be transformed to the background energy state. So, yes, so here are some results. So first, I point out a nearly perfect energy conservation for the DNS. You can see the total energy being conserved in the, I don't know if you can see my mouse, but you can see on the left, you can see the energy conservation line, and it's nearly perfect for the DNS. Then now we can focus on the quick drop of available potential energy connected to a rapid increase in kinetic energy. So this flip is produced by the strong vertical buoyancy flux. You can see the green line on the right plot. And this process is basically used by the current to transition from a laminar to a turbulent state as the current establishes itself and following the removal of the gate. On the other hand, we can observe that relatively slow increase in PB when compared to the other quantities. And this is the product of very little irreversible mixing taking place. You can see the brown line on the right. And again, looking on the left, after the peak of kinetic energy, both available potential and kinetic energy show a steady decay. And this comes along with a strong increase in the internal energy due to the turbulent activity. You can see the brown line. And we can also see that the irreversible mixing rate decays with the viscous dissipation, and a large portion of the energy is still stored as internal and will be later diffused to PB by phi, which is steadily increasing. You can see the purple line on the right. Okay, so I'm nearly. We also looked into dilution of the head and mass balance, but I will skip this for now and conclude. But you can see that most of the models are, especially the DNS, who have a very good conservation, and the SVV is capable to give a better mass conservation. Okay, so we successfully reproduce an experimental current at high Reynolds number, and to our knowledge, this is the biggest gravity current simulation reported in the literature. We compared instantaneous and average quantities, also achieving mass and energy conservation. We employ an extended energy budget to analyze how the energy flow with the development of the current. And overall, we found that all LES models are enough to reproduce the main features, showing the SVV better overall performance, especially in near wall. And it's also much cheaper because we have no filtering on extra terms. For reference, static Zmagorinsky and dynamic 1.8 times and 2.5 times more expensive given the additional operations. So we can see SVV has a promising future for simulations at much higher Reynolds number. We already reported values, I think, around 136,000 for an axisymmetric release. And we are now reaching the potential to, we have the potential to reach real life parameters, and why not a Reynolds 1 million? Yeah. So thank you for your attention. And I show again this picture of the current Reynolds 1 million. And now I can show also a little video, but if you have any questions.
Thank you very much, Ricardo. You're lucky you are the last speaker before the break. So you took longer.
A little bit later.
Yes. If you have any questions for Ricardo, please use the chat. And can you put your videos on, Ricardo? So we have a couple of minutes.
Okay, can you see it?
No. We can see your screen. That's all. Your slides.
Okay, let me see. Can you see it now?
Yes.
Okay.
Very good. And while we are playing this, there's a question. And how did you decide on the nu zero of a new parameter for this work?
Okay, so we did a sensitivity study, and we also used the Paul-like extrapolator to get a value. And somehow, even though the Paul-like is it's designed for isotropic turbulence, we found that it's probably the best value for our case, given the mesh resolution we used.
Thank you. I'm going to put the link of the paper for this. So in this paper, you will have some explanation how to choose nu zero of a nu for homogeneous isotropic turbulence using the Pauw-Safman closure and the Lin equation.
Yes.
Can you put the video again, Ricardo? Thank you. Very nice. Right, it's going to be a very nice way of ending this first session. So thank you, Ricardo, again. I think now it's time to go away from, can you stop sharing your screen, please? Yes. Now it's time to go away from the screen.